Today I'm going to talk about briefly about gravitational waves, their detection, detectors, and I've been told by some of you that I should bring in some mathematics, and that will be done, but without GR. So let me try to do that. Okay, so that will be slight plan of this part of the presentation, and then I'll pick up another PDF for some equations. So we will try to give you both physical and mathematical description of gravitational wave without bringing in GR. We'll talk about this famous transient events, and we'll talk about how these instruments work and what are the near future possibilities and why we are here for precisely that reason. Okay, so this is, I have taken some slides from the popular talks and I kind of mix and match them. So it's going to be a bit less different than what you might have heard in the popular talks. So the game of why we are so excited about gravitational astronomy is that we are opening a new window to the universe, and we knew from earlier epochs that the universe looks drastically different whenever we're able to open a new window, like the optical one we are familiar for the last thousands of years, and in the last 50 years or so we were able to open up other windows like in radio after the Second World War, infrared X-rays and gamma rays. Clearly, the universe looks very different. What we are trying to do now is to open up the dark sector of the universe, the dark side of the universe, and that's where electromagnetic events may not be the final say in that. And these days we have this slew of events from LIGO-Virgo collaboration. These are the gravitational wave events, and so that's one of the shortest events. That's the first one, 150914, and this is the longest one, which is 170817. So we have a dozen, and I'm sure that these days, if are in Facebook, will be bombarded with events from Grace DB, and so in contrast to electromagnetic astronomy, we are actually hearing these events, and I will put that. I'm sure that you heard it thousands of times, so I'm going to put it again. Oh, sorry, I think I'm not connected the. I'm sure that you heard this, right? Okay, so that's good enough. Exactly. I'm sure that's and this is what we actually heard back in 150914. So this is frequency versus time. We saw a signal which only lasted around 200 milliseconds, increasing both in frequency and amplitude. And the claim is that that actually represents merging black holes. And that's how we are going to explain, which you have heard many times. So this is, going back to those observations and their deductions. I'll talk about something which you may not be familiar, that has an implication for PTA. So that's what I'm going to do. The way I'm going to progress. Okay. So again, it's 101. No GR for the time being. So if you are going to look into gravitational waves, let's go back to Newtonian gravitation and ask what are the observational consequences of gravitational interaction. And Isaac Newton definitely knew that these are simply coming from the tidal interactions, and we know that there are 2 high or low tides per day. That's simply coming from the Newtonian description, and that's the real observational consequence of a non-relativistic theory for gravity. And what Einstein did was essentially to give a field theory description for tidal interactions, and that's where he was forced to introduce a space-time, which you are familiar from the special relativity, and then allowed it to curve. So instead of talking about trajectories and forces and other things, you can actually look for trajectories in a curved space-time to describe the trajectories of planets and any other complicated things. More importantly, this is the relativistic field theoretic description, and I'll give you briefly in that. So essentially influenced by Maxwell, Einstein was trying to give a field theory description for gravitational interaction, and back in 1916 he was able to linearize the system and show that it allows wave solution, and these were essentially the gravitational waves. And this is the cartoon I'm sure that you have seen, the perturbing a spatial slice by passing gravitational waves. So essentially for practical purposes, these are tidal forces propagating with the speed of light, and that's the classic description you heard about, ripples in the curvature of space-time. We will try to bring in some mathematics to describe these things. So, okay, those were the physical description. Can you do something better than that? So the problem Einstein faced was, if you look at the Newtonian description, you have a Newtonian potential. So you have a source distribution in kind of enclosed in an area somewhere. That's the y coordinate, shows you the extent of the source. And if you're interested to know the gravitational potential at a field point x, this is the integral for that. But if you look at this carefully, you will actually see that the changes in the matter distribution propagate instantaneously to the field point, and that's not very nice because it violates the basic tenet of special relativity that any information, so gravitational interaction carries actually information that should propagate with the finite velocity, speed of light. So we need to worry about it, and that's why this field theory description was constructed by going beyond the special relativistic consideration. But we can actually do without going into all that. And this is essentially a stole from a beautiful article by Bernie back in '84. So the game is that you go into Newtonian gravity and introduce the influence by special relativity, introduce this retarded time. So it's your Newtonian potential, the one we are familiar, but you now introduce a retarded time, and we will work out. Actually, this is all it requires to get most of the basic, quantities which we talk about in a gravitational wave seminar. So we will actually do that. So it's actually straightforward to show that this potential actually satisfies a wave equation. It's a scalar wave equation, so that's the only difference. And this can be an exercise, and it actually takes no time at all to do this. I'm sure that you are familiar with electrodynamics, I presume. So undergraduate students, that should not be a problem. And then what you do is that you actually go and I will do these steps in detail. I'm just trying to give you a flavor for what we are going to do. So the game is to actually evaluate this so-called relativistic potential, which is a scalar potential, at a point far away from this source distribution. And then it's exactly like what we actually do in electrodynamics, Jackson or any other standard textbook. Then you actually can show that there will be a scalar radiation, and I will actually do this step by step. And that scalar radiation is essentially given by this expression. This stands for 2 time derivatives of the quadrupole moment. R is the distance from the source to the field point, and G and C are familiar. But if you actually look at this, it seems to be a very small quantity, obviously G divided by C4. And you can actually go and do this exact analysis in general relativity. What you do there is that you have to improve the special relativity metric you are familiar with, the Minkowskian metric, put to this gravitational interaction, HIJTT. And then if you do the workout, essentially you get some result similar to this. Modulo the slight difference here, again we will go into that. If you can work out this, this is what you get. Eta is what we call as a dimensionless mass ratio. So if you have two equal masses, two neutron star binaries, eta is 0.25. But if you can, then you scale this properly, you get cos 2 omega t. So I'm talking about two, I'm essentially considering a binary neutron star. They are in circular orbit with an orbital frequency omega. You get the amplitude of the gravitational wave going by twice of omega t. That's simply because of the quadruple nature of the source. And you find gm divided by r by c square. So it simply means that if you want high amplitude, well, you need to have the radius of the system, the radius of the binary should be comparable to gm over c square. Another way of saying is that the sources which are going to be interesting to gravitational wave astronomers are going to be massive. So you need to have some nice value for this. You want this to be around say 0.1 or something like that. And you can go and compute this for the sun, and you will find that, well, it's not going to be exciting for LIGO, at least LISA made. So it should be massive. It should be compact. This is what meant by compact. The radius of the object is comparable to gm divided by c square. It has the dimension of length, and it should have a varying quadruple moment. That's all it is. Okay. Don't worry about this. This is a longitudinal gravitational wave. That's what you get from a a scalar theory. But don't worry about it. Okay. So we'll go into the details now. So let's look at the gravitational wave spectrum, and that's what we are here. Well, gravitational wave astronomy is in its infancy, but we want to advance the field. So obviously we have hectohertz gravitational waves coming from LIGO. We usually hear gravitational waves of frequency around 100 hertz, going both sides of it. And eventually, when you are my age, some of the younger people here, my age, you will actually see space-based interferometer operating out there, and they will be sensitive to millihertz gravitational waves. And of course, as Maura was pointing out in the colloquium, very soon, when some of you are going to get your PhD, you are going to see gravitational waves in the nanohertz regime. And then we don't want to talk about this for the time being. You might have heard about bicep, so I will not go into that. But that will also happen. Okay, so that's the spectrum. So how do we pick up gravitational waves? So we give an estimate, but we want to know how do we pick up these things? Well, I told you tidal interactions, and I'm sure that this cartoon you have seen 1,000 times, so this is +1. So the most important thing is that these are propagating tidal interactions, and tidal interactions are not local. So you cannot do some sort of a gymnastic with coordinate systems to say that now gravitational waves, because tidal interaction by default are going to happen on an extended regime, extended region. Therefore, it's very difficult to move them away and argue that it's just a coordinate. And this has other implications. I'm not going to get into that. But as far as we are concerned, gravitational wave changes travel time between free particle, because free particles are interesting for gravitational astronomers, whether they are pulsars or they are LIGO mirror, they are the same essentially. So if you are interested in the current LIGO detectors, they essentially have free particles. These are a large mirror that are separated, they're suspended with complicated electronics, and the laser light is actually passed between them to see such deformations. why we need to do that is these deformations can be extremely tiny, of the order of 10 raised to minus 21. You can go and work out that expression I gave you in a couple of slides back, and argue that suppose you have a supernova explosion in the nearby galaxy, that H will be roughly of the order of 10 raised to minus 21. Okay, so, and this is the sketch of LIGO for all practical purposes. So you can see that I have essentially not bothered about a ring of test masses. I'm just going to consider one here, one here, one here. That's essentially good for me. And passing gravitational waves, because they are tidal waves, they're going to deform that configuration in certain way, and we use interferometry to pick up gravitational waves. And since I have no idea, I'm not an experimentalist, this is my 101 for an interferometer. We are going to operate, I'm sure that you're familiar with Michelson interferometer. For LIGO purposes, we operate them in the dark port, and gravitational waves are going to bring, fluctuating light, and that's what essentially you heard in that signal. Let me just run this just for the sake of completeness. I'm sure that again you have seen this. This is not mine, and as I pointed out, we've been picked up from LIGO websites. I'll give you another description of this down the line. So this is essentially what we call as the locking of the interferometer. So you can see that things are now gravitational wave come by, the destructive interference is gone, but you can get all sorts of, the cancellations are not there, you get extra light out there. Earlier the two waves were getting cancelled each other, but now not. But these are fluctuating light, and that's essentially what that movie was showing you. That's all we do. This is what, and these fluctuations are around 100 hertz, and that's the reason we can technically hear gravitational waves from LIGO. Okay, so there are two LIGO interferometers which are operational at that time during 1509-14. They were in the US, this along the diagonal, this is near in Louisiana, that's in Washington State. The aim was to pick up delta L over L, the so-called strain, around 10 raised to minus 20 to around 100 hertz. And these days we have two interferometers of LIGO consortium along with Virgo in Pisa, Italy operating, and they have been picking up events essentially once in a couple of days, and we are in 03 these days, and a network of 6 gravitational interferometers will become operational, say in the next during the next decade, including Kagra, LIGO India. And we should be operational. Actually, in this state of India, there will be an interferometer LIGO India by 2025 plus. Okay, so back to LIGO during O1. So what we usually do is to plot the amplitude. So it's actually called amplitude spectral density, logarithmic frequency interval. Don't worry about the technicality. This is essentially the frequency dependent strain of the interferometer as a function of frequency. These are all sorts of resonances where you are not sensitive at all, and then we were ready to pick up events which can cause strain of 10 raised to minus 21 or so, and that's precisely what happened on around 15:20 Indian Standard Time on Monday, 14th September 2015. So there were two events, and so this is the Hanford data and this is the Livingston data. And these interferometers, if you look around carefully, they are, you can see that they are not aligned, they are flipped by 90 degrees This is for data analysis purposes. So when you combine, we can flip and plot one over the other after taking care of the delay. They match one on the top. So this is the strain, which is of the order of few times 10 raised to minus 21, and it's the time I'm talking about 200 milliseconds. So this event was picked up essentially with a latency of 3 minutes, and this is what the observation is all about. So signal. So what we are plotting here is frequency as a function of time. That's easy to visualize. And so it's a time frequency plot. That's the technical jargon. So the signal increased both in amplitude and frequency, 35 Hertz to 150 Hertz around in 0.2 seconds. That's this 200 millisecond I've been talking about. The maximum amplitude that you essentially pick up because your interference pattern will actually tell you that 10 raised to minus 20 Hertz. So this is the important things about LIGO observation. We are sensitive to the amplitude. It's not a bolometer. We are not counting photons or anything like that. We are not getting gravitons and saying that, oh, we see gravitational wave. It's very different from in fact, similar to pulsar astronomy. Detections are done on software rather than on an instrument. So the argument is that the frequency increasing from 35 Hertz to 150 Hertz is sufficient to argue that this is because of merging of two compact objects. We don't know whether they are neutron star yet, and that requires a bit more calculation. This is something we have observationally verified. This essentially is the expression which gave Hulse-Taylor the Nobel Prize, that the frequency of the orbital period of binary pulsar changes due to emission of gravitational waves that can be translated into circular orbits. Binary pulsar was eccentric, but you can actually do this for circular binary. And then you get an expression for gravitational wave frequency, assuming it's quadrupolar, f dot as a function of f in this complicated manner. And what you get is, it has an amplitude, f dot, and you actually can measure both f and f dot from your observation. From your time frequency plot, you can actually figure out what is your f and what's your f dot. That gives you this combination of mass called chirp mass, this curly m. So we simply, by looking at the time frequency plots, we can estimate this using this formula, that curly m to be around 27 solar mass. There's no unknown in this expression. That's really amazing. This is, electromagnetic astronomy. There's only two. We do electromagnetic astronomy to get the distance as well as get the mass estimate. And that's very complicated procedure. But here it's straightforward. Sorry. And so this chirp mass comes like some eta which I showed you earlier. The maximum value it can take is 0.25 times total mass. So if you put 0.25 here, you find the total mass to be around 70 solar mass. And this is what the grand publication in the LEC, that's the famous paper out there. So what? And we know that these are, so we know we are looking at a system whose total mass is around 70 solar mass. Okay? And what else? Well, the system definitely, went from 35 Hertz to 150 Hertz in gravitational wave. So assuming this is quadrupolar in nature, I told you that's the two time derivatives 2 omega t, we can see that the binary should have reached an orbital frequency of 75 Hertz. Okay? We have seen gravitational waves at a frequency around 150 Hertz. Therefore, it's quadrupolar, that cos 2 omega t. We argue that the binary reached an orbital separation of 75 Hertz. Good. So now what you do is that we actually use this very nice formula, omega square r cube is gm, good enough. Then the orbital separation at that frequency will be around 350 kilometers. I asked the question, well, if you have two neutron stars, we definitely can come all the way up to 350 kilometers. There's no problem with that because the neutron stars are around 10 kilometers in size. They can definitely come all the way up to 350 kilometers. They will not touch each other. However, there's a problem. The total mass for a neutron star system will be around 4 solar mass. Give me 5 maximum. It cannot be 70. So then this system cannot be 2 neutron stars. Then what? Well, we can say that maybe neutron star black hole. In that case, the mass ratio roughly, put 0.1, 1.4 and 15 solar mass black hole. Roughly. We don't know that, right? But if you do such a mass ratio, it actually changes the value of eta, that's around 0.1. Then the total mass will be around 100 solar mass. But we have a constraint from observation of F and F dot that the total mass can't be more than 70. Therefore, we have no other options but to imagine and want to strongly demonstrate that these are actually black hole binaries. It can't be neutron star binaries. It can't be neutron star black hole binary. Purely from observation, without doing any Mach filtering analysis, these are essentially two black hole binaries, and they're most likely comparable. And then what we do, well, once you have, we can do go back to GR and construct a gravitational wave form expected from black hole binaries. And 200 milliseconds, we actually can do this in supercomputers, and we can actually get the waveform associated with that event. And you can see that the reconstructed from the template as well as from the numerical relativity, they match with each other. They essentially, and the total mass is actually not bothered here, it's a scale. So it essentially consists of a black hole merging, black hole binary merging, and then producing so-called quasi-normal modes, which are essentially the vibrations of a product curved black hole. And then one can estimate various quantities. But more importantly, the amplitude of the wave, that's what we are familiar. We are, remember, I actually estimated from this back of the envelope argument, which we will do again, amplitude of gravitational waves. I know the mass. Then all I can do is to actually get a distance from that. So I straight away get the distance of the source. And remember, when Hubble was launched, there were several years it was actually trying to look at variable stars in the nearby galaxies just to get the distance ladder under control. This observation will give you the mass, will give you the distance in a jiffy. And that's the exciting things about gravitational wave astronomy. In fact, the detailed analysis gives us that this merger of two black holes, roughly 36 solar mass and 29 solar mass, it lasted around 200 milliseconds. You put that in the amplitude of the gravitational wave, which I just flashed around in one of the slides. We'll go back to that derivation again. It's around 400 megaparsec. It's pretty nearby for practical purposes. It was a very strong event with the signal to noise ratio combined around 24. And the possibility that it's the false alarm is 1 part in 10 raised to 5. Those are, so, and I'm sure that you have seen this, I'm going to miss this. So this is what we actually saw. Okay, so what's so exciting about it? It's an exciting event. I'm sure that you heard about it. It's the first direct detection of gravitational waves. We have and it's the first direct observation of black holes. It's the first direct detection of a binary black hole, and of course it's the place where we were able to test relativity. Well, it's a 10% test, so it's not spectacular as binary pulsar, but still it's the test of general relativity in a very dynamical regime, so that's very nice. And I'm sure that how many of you are familiar with this system? I'm sure that all of you are. Of course, the indirect evidence for gravitational waves came from 1913 plus 16. And these two gentlemen got the Nobel Prize back in 1993. And we know that indirect evidence are essentially around 0.2% consistent with GR. However, how many of you can explain this figure? I'm not looking at the students. This is non-trivial figure. And I always find people flash it. This shows that it actually shows cumulative period shift in seconds along year. These data points are observations, and the theoretical curve is given the blue. And it's coming from a pulsar observation. We only see one pulsar. You see something going around like this. The theoretical curve you can imagine coming from GR. It will have no information about pulsars or anything. It will have two masses, orbital period and eccentricity. So this plot is an amazing thing simply because you see, I'm sure that many of you, even students, have seen this. You know, it's just a pulsar. It just rotates like that. It's actually a double pulsar. Yeah. This is observation. You see this pulsars coming to. From that, how do you estimate two masses? Right? In electromagnetic astronomy, getting mass is a pain in the neck. And there are no error bars here because the accuracies are so fantastic. So this is something I want some of the younger people to, just people flash this, but there's a huge story behind it. I'm very excited to, catch me if you want, okay? Because you can ask this question. We have been seeing binary stars for the last 100 years or so. We could have done all that with the binary stars. No problem, right? It's not that easy. So it's a huge thing in that curve. So I want some of the experts to go back and, I think Shapiro-Tukolsky as one of the appendix explains this beautifully, but there are other places too. Okay, so this is the first, but we have indirect evidence for black holes, especially in the galactic center. These are not cartoons, they are actually positions of these stars moving around the galactic center. So we actually know that black holes indirectly exist out there in the universe. And of course we can test GR much accurately, not at the 10% level, but with the double pulsar we can do, but the regime is pretty weak. It's V over C of the order of 10 raised to minus 3. Compared in the case of GR, gravitational wave, that's essentially 0.5. Okay, so, but nature was out there helping us. There were plenty of other surprises. Okay, so so this is obviously the next big event. So it's 170817. I'm sure that you heard about it too. So I'm going to skip this very fast because I need to get into other things. So this was the first event where actually saw a gravitational wave event which lasted around 100 seconds, followed by a gamma ray burst, and that's essentially what this is all about. Okay, so this was the light curve immediately after, essentially 1.74 seconds after the merger of this, after the disappearance of the signal from the LIGO. We know that this is indeed a classic example of a gamma ray burst. It's actually a weak gamma ray burst, but there are reasons for that. In fact, you can actually do, especially back of the envelope, arguments to show that a black hole most likely formed 1 minute after this event. So people have been pushing things, and these are not really dependent on detailed simulations anymore. Okay, so and this was becoming a big industry. It's essentially opened up a new era of multi-messenger gravitational astronomy. Within 11 hours of that event, there was an optical observation of its candidate in electromagnetic observation. This is optical, 1 meter telescope back in south. And then of course it was followed up, including observing from the GMRT and many other radio telescopes, Chandra, VLA, and these are all optical telescopes, and this was the big event a couple of years ago. And then I'm not going to show this. Okay, let me now jump a bit. So the question is that even though I talk about this, I'm convinced that many people confuse, especially young people, confuse about the gravitational wave detectors altogether. So the argument is that we have an interferometer, and general relativity says that passing gravitational waves will actually deform, as the cartoon I showed you, and interferometer arms in essentially in contrasting ways. One arm is skews, the other one is extended, and that's good enough to pick up gravitational waves. But this is where the confusion. But we know that gravitational waves, in fact gravity actually affects photons. This is a famous experiment, right? You get photon getting redshifted. You can get blue shifting too. So in fact light is not treated as a static ruler. So the argument is that fine, the arm of the interferometers are getting skews or stretched by passing gravitational waves, but we are using photons, light, to pick up gravitational waves. But if the light is also getting stretched, we are not going to see anything. So if you have a ruler, of course it's a small measurement, but the ruler itself is getting influenced by passing gravitational waves. How are you going to make any measurements at all? This is always going to be a problem, and we need to think about it, because the PTA, we argue that pulsar signals are blue shifted and red shifted. This actually happens in the case of LIGO too. So if the arm lengths were stretched in the same way as our ruler, we are not going to see any gravitational waves. But that's not the thing we are talking about here. We are not using light as a static ruler. In fact, light is actually redshifted and shifted by passing gravitational waves, but because of the quadruple nature of the gravitational waves, these redshifting and blue shifting are different in different arms. And that's important. Once you have that under control, you know that it's impossible to create destructive interference by superposing lights of different frequencies. Remember, you need a monochromatic source to get interference pattern. So here essentially one way of thinking about is that light is indeed getting blue shifted and red shifted, but it doesn't really matter. It's propagating in the arms. In order to show you more about a cartoon, I will go and this is something by a friend of mine, Marcus Foster, is an AI, was an AI. So instead of explaining how interferometers work, I'm going to put this cartoon. So this is an interferometer, as you can imagine. That's the light. So instead of putting passing light, I'm going to put particles. So particles can actually stand for the wave maxima at a given point. Okay. So you can see that two waves are coming out from here. They're getting, one goes this way, the other goes this way, and they come back. And you actually, because in order to demonstrate the effect of delay in this, you make it slightly larger. So, but what you can see is that both green and red bullets are actually equally spaced when they come to this, light detector. That's what I want you to, stare at it. You will actually see that. So this is another way of saying is that the interferometer is actually operating in the dark port for the time being. Now we will bring in the next one. So now gravitational waves have been present in the system now, but now look at this. You can actually see that sometimes these particles come even together. You can see that. So, and remember this blue, see this green and red particles are essentially for the maximum of a wave. if that's the case, you can actually see that sometimes they add together, sometimes they cancel each other. Another way of saying is that passing gravitational waves change that equidistance between maximum and maximum and minima along these two directions, and that's precisely what we are seeing as gravitational wave. This will cause destructive interference, light will come out. Okay? And well, I can put it in another way. So these are equally spaced dots, no gravitational waves. When gravitational waves are passing by, can we actually see that, this is time essentially, so you can actually see that now they are no more equally spaced. They can combine, sometimes they will be very different. So the spacing between them differ, and that's precisely what we actually do in the pulsar timing array. These dots are essentially pulsars from individual pulsars, and passing gravitational waves are going to change this. Okay? So, and that's why the time to get into gravitational wave in the nanohertz machine. These are exciting. Well, we are expected to get a background, but more importantly, we can even look at gravitational wave eventually when it matures with redshift of, look at that, this can be a redshift of 100 and other things. It's amazing. It's possible to pick up sub-microhertz gravitational waves. And of course, this is the pulsar timing array. We will briefly get into that too. And there are several operating pulsar timing arrays, which is Sparks, Nanograv, European Pulsar Timing Array. That's part of the IPTA consortium. And of course, now this Chinese Pulsar Timing Array, South African, Indian Pulsar Timing Array is also coming up. And again, in contrast, I just want to show you this rapidly. So, passing gravitational waves are going to, move the distance between the pulses. And that's precisely what I showed in that cartoon too. So this is the gain. And so hopefully we will have that. I'm going to pull this back because I haven't shown you the equations part. So let me put that. I'm going to, again, so I have to rush a bit. Okay, so the game is that how do we do gravitational waves without invoking general relativity and try to get the estimates. Maybe I will leave these things later. We'll try to go into why we expect a background and other things. So this is the very nice article, but I have added material into this. Okay, so the game, as I pointed out earlier, is that look at the Newtonian potential and bring in the retarded time. So that's the game. Now, what do you do with this? Well, so this is your retarded Newtonian potential. And what do you do? We can, in a straightforward manner, argue that it actually satisfies a scalar wave equation. Now, look at this expression. Take a gradient of that. So what will happen? There will be two terms. There will be a term which goes like 1 over r cube, and then this is coming essentially because I'm going to take a gradient of that r in the retarded time. Get two terms. So what? Okay. So remember that r was essentially, this r is essentially x minus y modulus. So what I will do is that I'll consider a field point which is quite far away from the matter distribution, and I'm going to dot that grad of phi with n. N is the point vector in the direction of the field. So I get n dot del phi, roughly of the order of dou phi divided by dou t times c. So in another way of saying is that I have far away from the potential, which is a so-called retarded Newtonian potential, the typical length scales over which this potential changes is essentially given by c times typical time scale over which the phi varies. Okay? That's essentially a gravitational wave for all practical purposes. It's a property of the wave. Okay? Typical length scales over which certain quantity varies, if it's given by c times the time scale over which the quantity varies, that essentially is a definition of a wave. And here is a wave that propagates with c. Of course, there's no gr here. Everything is put in by hand. Now, Newtonian potential is like v square. So, if I want to get the amplitude of such a wave, just have to divide this by c square. So, all I need to do to get the amplitude of the gravitational wave is to look into the time dependent part of this potential, divide that by c square. That's all. Okay? And how do you do that? This is the thing we have been doing all along in electrodynamics. Look at that expression for 1 over r, which is there in my potential, which is essentially 1 over x minus v modulus. I expand it because I'm going to consider a field point which is quite far away from the source. So I get the leading order term 1 over x, and then I get y dot n divided by x square. I'm going to ignore other terms because I'm looking for a propagating wave which goes like 1 over r. So my potential is something like this. Very nice. So, but I have the retarded time here. I can do exactly the similar expansion there. And I'm going to expand. I'm going to consider, I'm going to insert this tr. I can write roughly as t0 minus y dot n divided by c. It's very easy to do this. In that case, I can actually expand my phi of r in so many ways, one term after term. Okay, so I get 3 terms. Very nice. So what? The first term is integral rho dqy. That's essentially the total mass of the system. What about the second term? Well, I have rho dot yi dqy dot ni. I'm just rewriting n dot y as ni yi. But that's harmless term for me because I can use continuity equation to take the derivative of rho dot onto y dot. Dou rho by dot t is the same as del dot j equals 0. I do the same thing and then integrate over the volume. Then I get that as ni rho vi dqy. This is essentially n dot p. This is essentially the momentum of the source distribution. But in in gravitational interaction, two-body systems especially, this guy has to be conserved. So that term is not going to be bothering me at all. Then I do the third term. I do exactly the same argument rho double dot yiy j d cube I. I do the continuity equation a couple of times, and I can rewrite this term as iij, the quadruple moment, 2 time derivatives like this. This is the quadruple moment. So I get the retarded potential becomes like this. This term is no interest to me. This is not a propagating effect. It's just a 1 over r potential. This anyway doesn't care. And this is of interest to me. It goes like 1 over r. It is time dependent. That's all. That's all I care. So that's the analysis I was talking about. And I said amplitude of that wave is essentially given by, take that part divided by c square. This is what I get. But there are problems here. Here the amplitude of the wave depends on the quadruple moment time derivatives dotted by ni and j. That's the line along the unit vector along your line of sight. It's a longitudinal thing. That's okay because I'm talking about scalar waves here. The GR changes the picture because it's a field theory. GR, this is actually going to be transversal in nature, so that's no big deal. And in fact, when you make a comparison and if you do a proper analysis, the amplitude of the gravitational wave is essentially given by this expression, which is fairly identical to this. This mod of x is r. So you get g and c4 under control. 2 goes up, it's okay. And I get slightly different object. It's a trace field under transverse. It's not longitudinal anymore. But that's it. And this is all enough to argue that if you have it's a quadruple moment, and if you have a spherically symmetric distribution, there will be no time derivative to that, the quadruple moment, so no gravitational waves. And then this I will skip for the time being. I can actually estimate the gravitational wave luminosity in exactly similar to the electromagnetic wave, and actually can argue that the luminosity of the gravitational wave will be given by 3 time derivatives of the quadruple moment square. You put g over c5 from dynamical arguments, and then you actually can work it out. Then you will find the luminosity of gravitational wave is given by the Schwarzschild radius, which is essentially gm over c square divided by r square v over c raised to 6. But L naught, look at that L naught. L naught is c5 divided by g. Amplitude of the gravitational wave was g over c4, but the amplitude of the luminosity of the gravitational wave source is huge, c5 divided by g. That's of the order of 10 raised to 52. That's precisely the reason that these are the most violent transient events in the universe. And if you have a system whose radius is comparable to the Schwarzschild radii, that's black hole binaries, and the velocities are comparable to c, indeed these are copious sources of gravitational wave for us, and that's precisely what LIGO is demonstrating these days. And that will be the case with our nanohertz gravitational wave observatories. Okay? And now, but you might have heard that the nanohertz gravitational wave astronomers are expecting a stochastic gravitational wave background, not individual events for the time being. Why? It's actually, so first thing, I'm just trying to make this a bit of mathematical. So again, passing gravitational waves are going to affect pulses coming towards us, exactly like the cartoon I showed you. And since we are going to use pulsars as our probe rather than test masses, so you can, or practical reason, you can imagine that the Earth and the pulsar is essentially one arm of an interferometer. You have several arms for all practical purposes, and then therefore what we are interested is, you monitor the, as Tim was talking about yesterday, you try to model the rotational, every possible rotation of the pulsar so accurately. So if you can't fit that, gravitational wave will manifest as timing residuals. But interesting thing is that since you have one arm consists of Earth and the pulsar, there will be an Earth term and then there will be a pulsar term. But then the distance between them, or time difference, can be substantially different. So you have the geometrical time delay coming into the picture. But all we are doing is a passing gravitational wave changes the essentially the spin, the observed or measured spin frequency of the pulsar, and this can be worked out fairly straightforward manner. So again, this is I'm not going to do this derivation. In fact, it's actually fairly straightforward to do this. You don't even need to know in order to explain this for the LIGO, you need to figure out something called geodesic deviation equation. I only need geodesic equation to actually derive this. I will not do this derivation, but catch me if you want. It's fairly straightforward. The point is that passing gravitational wave changes rotational frequency of a pulsar in a very specific manner, and those changes are going to be depending on the strength of the gravitational wave here on the Earth and on the pulsar, and integrate this expression over your observational span, you get the timing residuals. And the claim is that, or what we really hope is that we will see a stochastic background of gravitational waves, and these are caused by a cosmological population of massive black hole binaries. Why do you think that it will be a background? Why can't we see individual black hole binaries? The argument again is fairly straightforward. So the argument is that suppose we want to know how many such sources are going to be there in a frequency interval delta f. We usually have delta f as 1 over t observed. That's the time of observation. It can be a decade, for example. Then I can write delta n to be dn over df times del f. I'm doing mathematical gymnastics here. This I can rewrite as dn over dt times df over dt raised to minus 1 times del f. But this is what we just used in the last few slides back, an expression for f dot. I'm just going to bring that one right here. Don't worry about g's and z's, I can all serve proportionally. Okay, so I get delta n as dn over dt times this quantity times delta f. Now you ask this question, it's a fairly straightforward. It's around 10 raised to 11 galaxies in our universe, and you have seen Hubble pictures of merging galaxies. So imagine that there will be a galaxy will experience at least one merger in its lifetime of the universe. Hubble time 10 raised to 10 years. If that's the case, 10 raised to 11 galaxies experiencing one merger in its lifetime of 10 raised to 10 years, then dn over dt will be 10 mergers per year at least. Okay, you put it there. So then you scale this. This is something astrophysicists do all the time. You get, and then delta f is 1 over t observed. So if you put the chirp mass around a billion solar mass and observational frequency around 10 raised to minus 8 hertz and t observed around 10 years, and assume there are 10 mergers of big black holes per year in the universe, then you find the number of sources is of around 10 raised to 12. So you can change all these numbers up to you. You can make it, well, don't go up to 10 raised to minus 12 mergers per year. You will find that the delta n will be more than 1. Therefore, we are not going to see individual sources, but you will see a diffuse background in the pulsar timing array frequency, and that's precisely what we expect. And it's actually easy to characterize this object, this background, in terms of an amplitude, just like the LIGO we have shown, h as a function of frequency. That's the plot I've been showing, the bucket, right? So that can be as an amplitude and a frequency raised to minus 2 over 3. Again, watch over this 2 over 3. This has again, based on the fact that you have omega square r cube is gm, it's a derivative of that, and this is what we expect. And for example, nanograv and IPT are all going to constrain this amplitude of the order of 10 raised to minus 15 and other thing. That's precisely one. And again, this derivation is not that complicated. Do I have some more time? Okay.
Yeah, you still have a half hour.
Oh, really? Oh. Oh my God. I should not have.
You got lots of time.
Oh, I thought it's 10:30, so I should.
That's good. We have lots of time to ask questions.
Okay, sure.
Lots of questions.
Not a problem. I could have made it 2 hours, but I kind of rushed through. I'll go back slowly then. Okay, very good. Thank you. Okay, so how do you know that? Okay, so this is essentially a beautiful paper by Finney. I'm just extracting one part of it. So how do you know that? Well, this is actually not meant for PTA, but doesn't matter. Arguments are the same everywhere. So we need to obtain an estimate for that HC. How do you do that? Well, just follow the arguments with me. So again, it's straightforward. Keep telling this. Let EGW be the current energy density in gravitational waves. But now what I do is that I'm going to define an omega GW. Again, these are influenced by cosmological consideration. So there is a bit of cosmology inherent in this. So define that omega GW to be a ratio between the present day energy density per logarithmic frequency interval. This is the jargon people use for df over f. You can imagine that d of log f is essentially that. Okay, so that's the ratio. Omega GW is defined as a ratio of present day energy density per logarithmic frequency interval, of course in gravitational waves, to the rest mass energy density, which is rho c square, that will be required to define, to close the universe. So that can be easily estimated if you have done a course on cosmology. So another way of saying is that EGW can be written as integral 0 to infinity rho c square omega GW df over f. Essentially, this is logarithmic frequency interval written mathematically. Okay. Now we need a slightly more consideration here. Suppose, again, cosmology, we have something called co-moving volume. It's nothing big deal. It's a measure of volume while we consider the expansion of the universe. So that these things remain constant, number density for example. So let n dc is the number of events in a unit co-moving volume in a redshift between c and c plus dc. Then EGW can be written essentially as this number density. This is EGW, is essentially the every merging event will emit certain amount of gravitational wave, that's EGW, in a redshift. And this 1 plus c comes from cosmological consideration. Well, I need another lecture for that, but I'm not going to get into that. But you have to buy this for me. So I can rewrite this DGE, the energy emitted in gravitational wave, as this ratio. So DEGW divided by df by f multiplied by f. It's just a mathematical gymnastic. There's nothing going on here, but I need to do this because I'm going to compare that df over f, and that's the game. Okay, so it's beautiful. It's just playing around with it. It's physical. You can make it highly mathematical if I want, and of course, because I'm considering cosmological consideration, there's a cosmological redshift being acted upon here. That's it. Okay. So now, what do I get? I get then EGW to be this double integral. But we have already argued that this quantities should be identical to rho c squared omega GW. Again, logarithmic interval. I just equate these two expressions. I get this quantity. That's pretty much all I want. So the energy density per logarithmic frequency interval is essentially equal to the co-moving number density of the events times the redshifted, that's the one, energy per each event in the logarithmic frequency interval. Again, df by f is the logarithmic frequency interval. That's all. So I get an expression for that. This I can actually evaluate for anything I'm interested, especially for binary black holes. That's precisely what I do. I can compute dE by dF if I have a merging black hole binaries. How do I do that? Well, we just did this in the sense of this is essentially dF by dt, and then this is dE by dt. Take the ratio, and therefore you actually find curly m again coming over there. When I plug that one into this expression, and because of this 1 over 3, I get a redshifted thing, and this has to be this has to be integrated over. That's the reason I get this average quantity here. So essentially, I get an omega gf, which goes like 5 over 3 f raised to 2 over 3. That's all I care. So this is my expression for omega, but omega is some sort of an energy density. I want to connect that to an amplitude, and that's again straightforward. So again, this is the definition. This is again based on LIGO consideration if you want to think about it. So what I did was omega gf df by df. I'm going to rewrite this in terms of f square hc square f df over f, again by construction. So this will be the characteristic amplitude which causes the same energy density in logarithmic frequency interval. So I can read off now. These are the two expressions. I already derived one for omega gf. Then I get hc, the characteristic amplitude. I have all sorts of power raised to f raised to minus 4 over 3 and some quantity. Everything else is essentially my ignorance. I have no idea about n naught, which I can cook up depending on all sorts of cosmological evolution of black hole binaries and the relations and all that, which is what Alberto, Susanna and many others are doing. So all this ignorance I can put as an amplitude, and I get exactly the same power, which is the square root of this, which is 2 over 3 minus. And again, this relation is again going back to omega square r cube is gm essentially. So I get the strain amplitude, and this is what nanohertz and gravitational astronomers are trying to see, whether do we have that. I'm not going to derive the curve because that's a bit more involved, but essentially this is what I want to say. There, I'm run out of my slides. So, and I should have thought about this carefully. Okay, that's it.
Questions?
Yes.
Okay, this is probably a result of my lack of understanding of gravitational waves, but I thought the part of the reason you have to have the interferometer to observe them is because they're not localized, you have to observe them over a distance. So how is the light affected by the gravitational wave? Like how is it blue shifted and red shifted?
Yes, gravitational waves cannot be measured doing local experiments. That's another way of saying, as you might have heard about, that I can, in the local point, I can put a, Minkowskian consideration. There are no gravitational waves there. However, these are, as I keep telling about the tidal interactions, because the tidal interactions are behind what I call about this, I told you about geodesic deviation, if you're familiar with that. It's essentially a tidal, so a tidal, if you are freely falling particles in a tidal field, a differential gravitational field, then their trajectories will be affected. Now, these are for particles and it's also applicable for photons. It's exactly the same way. It's the same as, it's a dynamical way of thinking about what's this experiment, Pound-Ripka experiment, where the photons get, you actually measure redshifted, in the lab frame here and go to the top of a tower. And if you have X-ray photons, you can actually see slight change in their frequency. It's exactly the same, but time dependent. And for all technical, well, Rana will never like that, but they are getting redshifted and blue shifted in, different arms differently. Hence, destructive interference. Hence, signal. Yes.
Oh, I have two questions. One is, what's a dark port? And the other one is, what does LIGO actually see? Are they, you showed the dots that sometimes align and sometimes don't align. Are they actually watching fringes appear and disappear, or are they watching fringes move? What do you actually?
Okay, sure.
What does it actually look like?
Okay, I should be careful about giving these talks and getting away with it. Yeah. So Yeah, so my understanding, this is all I learned from people rather than doing anything. So, yes, for all practical purposes, this is what we are going to see. This output of this is the dark port. There will be no light coming out of it because the waves along these two directions interact destructively. So the dark port means there will be no leakage of light in the output port or in the photodetector. So that's the dark port argument. So I think the cartoon shows that. So again, once you have in the lock, you will actually see this is the adjustment they are doing to make it work. Once they are in that configuration, now you can see that the crust and trough are cancelling each other, and that's the dark port. Okay?
So you're saying that
destructive interference at this point.
Gravitational wave,
Exactly.
then there
Yeah.
will be no signal.
Now, passing gravitational wave, you can see that light fluctuates. So the photon you count is a bit more than that, and these fluctuations can be translated as a time frequency plot. And actually, Rana showed us something. You can actually listen to interferometer, and if you're good enough, you can say that they are essentially in log. So they do all that. Because this disturbances can be translated. All things we are going to see are on audio frequencies. So he has the knack of listening to gravitational waves. So yeah, that's essentially the point. So dark port, no stray photons will be there in the photodetector. Passing gravitational wave, other disturbances, anything. So, but now what you are looking for, there will be always stray photons, but we are not interested in just that stray photons, but the intensity of those photons varying in a certain manner. That's the point.
So what is the value of the capital omega GW? And can it change the result of cosmological standard model significantly?
Oh, it's already there because that's what I pulled out, right? I mean, I said rho c square, that's already the standard cosmological consideration. So again, that omega GW is going to depend on how many black hole binaries you expect to merge in the universe, how they expect it to merge, whether they are going to be eccentric, this, that, all those considerations. This is this big, I'm no expert on that. So that omega GW is going to depend on, how many, that integral n0 I talked about. All those are our ignorances. So, but its frequency dependence is well known to us if you are considering purely black hole binaries, which is of the order of that 4 by 3 minus 1 over 4 by 3. So amplitude, not sure. Frequency dependence, very well understood. So you don't need templates for that.
So I have two questions. One was how do you relate the fluctuating intensity of the light to the gravitational wave strain? And the second was, what does the co-moving volume or number density exactly mean? I didn't get that.
Okay. Second question is it's a cosmological consideration. I have to give you a course on that. Other than it's essentially see, you have to define a volume when you have an expanding sphere, for example, as in the Hubble expansion. So co-moving volume allows you to consider quantities, so the number density, for example, of certain things which remain constant in this co-moving volume. So it's easy to deal with Otherwise, you have to worry about, it's essentially dou rho by dou t. Because of the expansion, you don't want to worry about that. Hence, we consider co-moving volume. Is that good enough? I don't know better way of physically.
Expanding as well. That's why everything is constant. The number density. The volume.
Yeah, I want a very specific volume measure in cosmology, so that physical quantities like number density, if they are conserved, they don't change in time. Okay, so is there a better way of saying this? I don't know.
No, I don't think that I would understand it if we were specific, because I don't have a knowledge of cosmology. The first question is the main doubt. How do you relate the?
Sure, not a problem. Okay, so so good. So now the interferometer works because, for practical purposes, the arm lengths are changed, right? Now the arm length, if you remember, we go back to this nice, so this is essentially your interferometer. This stretching and squeezing are directly proportional to the amplitude of the gravitational wave. That's the h I derived. Okay, so the intensity of the light I'm seeing there, not the frequency, intensity, is essentially directly proportional to the amplitude of the gravitational wave. Therefore, by getting those, how many photons I get and all that, not the way they vary in time, that's gravitational wave evolution, but this just the strength of the current, the photon, flux, actually gives me an amplitude of the gravity, because that's directly proportional to how much I can change the arms. Therefore, I get the amplitude, which is very, very rare in any astronomy. You always get the flux. That's what we are interested in, 1 over r, in electrodynamics. We are not interested in other parts when you expand your potential vector or scalar.
I guess the amplitude of the gravitational wave depends on the geometry, on how you see the...
Oh yeah, I have not bothered about it for the time being. Yes, of course, there are lots of unknowns, and because it's, of course, this is an instrument, and so I have to have the response of the interferometer imposed on it. We deal that as f plus and f cross and all those things, but consider them as some trigonometric quantities, maximum value 1. So worst case scenario, I can drop one polarization, saying that my inclination of the orbit is such that one polarization drops away, the other one will be maximum. So in the back of the envelope, I will not bother. Hence, we do a detailed, Bayesian analysis, which incorporates all sorts of possibility and all that, and then finally come up with a number. Hence, it's 10% accurate and all that.
So, about the localization of the sources, you said that they can be localized only if they're detected in one of the detectors and not detected in another one. So, if they're detected in both the detectors on Earth, so is there a way to localize them?
Can you repeat the question?
Okay, so the question was, how do you localize gravitational wave events? If you have only one, so it's essentially triangulation. So you have 2 interferometers, then it's easier because you can be anywhere in an arc. And this is slightly more than that, because it's just going to depend on delay, the observed delay between these events. And there's a geometrical delay of 10 milliseconds between 2 interferometers in the US. So the interesting thing what happened, so it's the triangulation. What happened for the BNS mess was, it was not picked up by Virgo. And that was very helpful to throw out one law. I went very fast through that, thinking that you all heard about it, so I didn't. don't know that I have. Yeah, sure. So this was, so you can see that you expect the gravitational wave to be seen in all the three interferometers. They were both, all three were operational in April 2017. If you use only two of them, as I told you, it's a stretch, it's a thin strip. So you get this and this possibility. This turned out to be southern hemisphere, this is northern. Both were possible. But we saw nothing on Virgo, which means that the configuration was such that, and this is where the angular configuration and where the detectors are going to be important. We see nothing on Virgo, which means it was in such a configuration that Virgo was not sensitive. Okay? And therefore, this was dropped. Nobody bothered to go and search for it. People were searching only in the southern hemisphere, hence they were waiting for 10 hours. Because this happened, early morning, so there was no time in Caltech to go and look for the northern observatory. So then waited for the southern observatory to come online. Okay? So that's the reason I said Virgo was, and of course this came much later, but anyway, yeah.
So my question is not just this, it's like, so even if, so suppose we detected into detectors
Correct.
across some distance apart, then is it like practically possible to localize the source by looking at the change in the configuration, the change in the mirrors and the way they interfere?
No. So once you detect it, once you detect it, this is what you're going to see. If you have two interferometers pick up, depending on how, sometimes this can be 1000 square degree, because these events are usually maximum a second, unlike this. So usually there will be patches in the sky because you dominated by two interferometers. Virgo helps definitely. So, yeah.
So I agree with you over the Hurst-Taylor binary pulsar, the decay of the orbital periods. In fact, from conversations I've had, right, even non-pulsar astronomers don't know much about it, and even and I'm surrounded by particle physicists in my institute, and they know absolutely nothing about it, despite the Nobel Prize. So anyway, my question is that pulsar still being? Are people still measuring the decay of that orbit?
Oh, yeah.
Because I know in 2022 or something it will go out of, we will no longer be able to observe it. And can we learn any more about GR from further observations of this?
I don't know whether 2022 anything special about 1913 plus 16.
Okay, I thought I read somewhere long
No, double pulsar.
No, not double pulsar, 1913D plus.
Yeah, so I think it's regularly monitored.
It is very good monitor.
Okay, Joe is not doing it, but students are. I'm sure that you know them more.
Actually, Marcus Lower in the background.
Okay.
Oh, I'm sorry.
Has been doing some studies of this, yes.
Joe Weisberg.
Oh, that's right, yeah.
Yeah, Weisberg.
16. Joe Weisberg's been observing it. Our students of his. Carl.
Right.
And they're
So.
measuring new relativistic effects all the time still.
It's constantly observed, John Gopakumar.
Right, but unfortunately there are no Shapiro measurements, so you have essentially Einstein delay to worry about, and then PB dot obviously. So in that connection, since I have time, I just want to, so what is this? This is amazing about is that this is what you measure. This is what you see. It's a pulsar coming towards you and going away. So the number of pulses per second will vary. That's essentially Doppler. From that, you get this beautiful curve. And when the Arecibo went out, there was no observation, but it came back immediately. So this is non-trivial. Just by seeing this, how do you expect the two masses to come out? So the technical term is that pulsar timing is equivalent to single spectroscopy, single line spectroscopy. But thanks to GR effects, we can break the degeneracies in single line spectroscopy. So we get not just the mass function, we get more complicated measurements. From that we extract two independent masses independently, and plot this curve. Plotting that curve is not trivial, and that's something amazing. I want young people to actually appreciate that. People just pass it by. It's amazing experiments.
Any more questions? Lita?
Yes.
Yeah. So with the stochastic gravitational wave background that we would observe with pulsar timing arrays, is there a way? I mean, I'm sure there's a way we can detect individual systems out of it. Is there a way we can localize those systems? Like if we see like, oh, this is too massive, this system, are we able to locate where that system might be?
Okay, so first answer, if you have one pulsar, very, very accurate pulsar, you can constrain possibility of gravitational wave coming from a given source. Imagine there's a source, and people have done it carefully. But if you want to constrain an unknown electromagnetically not observed, so if you have no idea where it is, you need many more pulsars. That's the reason you need an array. But I have seen papers talking about, I don't know how many pulsars are required, localization, but I am not sure whether what accuracy is. It can't be 40 square degree, that I know for sure. It will be much more broader than that, but then so once you know there are a binary, people can, and even if it's maybe 100 square degree, optical astronomers will try to look for them in massive galaxies, because we know that that's what they're going to see. It won't be outside the galaxy. So for example, if I remember correctly, LSST, which is the next big thing in survey, supposed to see such massive black hole binaries. I work on something related, at least few per year, along with Oumuamua objects. So, yeah.
Got time for one more question. More?
Yeah.
Oh, I just wanted to add something
Yeah, sure.
to your question. Two things. I mean, it's true that we'll have very poor localization at first if we're restricted to just using the Earth terms of our pulsar detector, right? So you talked about the pulsar and Earth terms. We can get very good localization if we know the positions to the pulsars, like within a gravitational wave wavelength, so within like a parsec, which could happen within sort of decades, right? That's not going to happen immediately. The other thing I just wanted to say is, I think probably like the first single source detection will be a follow-up of an electromagnetically identified candidate, right? So we're trying in the IPTA to like look for sources that have been identified, say in the X-rays or optical, and people think there might be evidence of a supermassive black hole binary there. And then we have we already know the location, right? And then we can search like at that location in our pulsar timing data, and that makes us much more sensitive. So that may be I think it's likely that will be the way that we first make such a detection. It won't be a blind thing that we're trying to localize, but we might be following up something that's been identified electromagnetically.
In fact, we ruled stuff out with that.
Yeah.
With Janeski.
Yeah, I mean, the first kind of gravitational wave astrophysics paper was published back in 1994, right? Right before actual astrophysics was done.
2004.
2004, sorry.
All right, I think we're about out of time, so.
Oh, it was actually really similar to what Maura was going to say. So.
Okay, so let's thank Gopu again.